Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will start to talk about neural networks for the first time in the course. Last time we covered a very simple example of supervised learning models, which was what did we cover last time? What did we cover last time? Linear regression. Okay, so 1D linear regression, which was really simple. It was just a line. Okay. And with that, we went through many concepts that are general to supervised learning, like training, testing, like loss function, right? Okay. So inshallah, today we will switch to another model. You saw that with 1D regression model, it is a bit limited, right? Because it's just a line. Not everything is linear in life. Actually, life is much more complex than that. So we would like to have a model that can map between, first it can fit to more complex functions, and also it can map between multiple inputs to multiple outputs. Okay, what we saw last time, it was just one-to-one. And we will see that inshallah today, that shallow neural networks, neural networks in general, can are flexible enough to fit much more complex functions, and it can allow to have mapping between multiple inputs to multiple outputs. So we'll start again very simple. We'll start with the simplest shallow network, which has just one input and one output. Okay, and then we can inshallah extend it with more inputs and more outputs. But let's understand first how one input, one output network works, and then we'll talk about the more complex ones. This is the equation for the linear regression that we saw before, right? It's a linear equation. How many parameters we have here? 2. What are these 2? The slope and the intercept of the y-axis. Very good. Now, here is an example of a shallow network. It's just a more complex function. Okay? Again, it is like linear regression. It's a function, as any model, by the way, it would be a function of the input and the parameters. Okay? Type. If you look at this equation, can you tell me how many parameters we have in this equation? So this equation represents a shallow network. Of course, we will understand how this works and what it means. But can you recognize here what are the parameters and how many are they?
10.
4 or 10? Why is it 10? So let's count them. Let me change this. Yeah. So what is the first one? Where is the first one? Phi 0. Okay. So any Greek symbols are the parameters, by the way. Okay. So phi 0 is a parameter. Phi 1. Okay. How about this? No. Why not? It's a function. We said that the function has a square brackets like that. So this is a function, and then this is a parameter. That's a fourth one, fifth, sixth, seventh, eighth, ninth, 10th. Okay, so we have 10 parameters here. Okay, 10 parameters. How many inputs?
1.
Which is x. Just one input, x here. And how many outputs? 1, because that's, if we know the values of the parameters, that will eventually be a number, and that's the one input, the one output. Okay. Yes. So a function that has that uses another function. Yeah. So A here is a function, and we actually call it an activation function. Okay. So A is for an activation function. Now, as you can see, the activation function is applied actually 3 times here, and it is usually the same activation function. And there are many possible activation functions that are used in neural networks. The most widely used of them is called rectified linear unit, or in short, ReLU. So the ReLU function is one of the very commonly used functions, and we will use it a lot, at least as an example in our course. Right. Let's look at this ReLU function first before we look back into the neural network equation. and understand how this function actually works. The radio function takes an input, and if the input is positive, it will just pass it. So here the input is z, okay? The output is also z if z is greater than or equal to 0. So whenever the input is positive, it passes as it is, as an output. Type. If the input is negative, then the output is 0. So it's like clips the output, the input, in the negative regions. Okay, whenever the input is negative, it's clipped to be 0. Whenever the input is positive, it passes as an output. So it looks like this exactly. If the input is negative, the output is 0. If the input is positive, then the output is exactly like the input. Whatever the values of the input is, will be the output. This is how the radio function works. Okay, so it's like removing all the negative parts. Every negative value will be mapped to 0. Okay, this is how the radio function works. Now back to the network, back to the equation, this complex equation. As you said, it has 10 parameters. Last time we talked about the notion of having parameters in a function as indication of the fact that it is a family of equations. It's not just one equation, right? Because with changing the values of these parameters, we have other functions. They have all the same form, but they are actually different functions. So the function that you saw here represents a family of functions. The values of the parameters determine a specific function of them. And if we know the values of the parameters, then we can compute the function. We can compute the output of the function, right? So given the parameter values, we can perform inference. We talked about that last time. When we have the values of the parameters, now given the value of the input, we can do inference, which means we can get the output of the function, or the prediction in this case. And if we have training data and loss function, then we can change the parameters to find the best values of the parameters that can fit the data or can minimize the loss function. Yes.
So last time when we had two parameters, it was a line.
Yes. It's much more complex. We'll see how it looks. Yeah. But all of these are just concepts that we discussed last time. So nothing new here. Now, what does it actually represent? That's the question that I just got. It looks very complex, right? So usually in computer science, when something is complex, we decompose it into smaller parts. But just in short, this is how the function will look like. Okay, eventually. These are just 3 examples of how this complex function will look like eventually. It might not, of course, look very trivial now, okay? But it will look something like that. Before we understand how actually this is the case, from the form or from the shapes that you see here, the 3 examples that we see here, we can say that the output function will be piecewise linear. Piecewise linear means it has pieces of linear functions, okay? Each region here is a linear part. This is what we call a piecewise linear function. Okay, it's connected pieces of lines, and all the shapes of the family of the functions of this equation will be like that. But which shape exactly, it depends, of course, on the parameters. Now let's see how we can get a shape like that. Okay. As I said, we will have to decompose it into small parts. So let's break it down. We will first break it down into 2 parts. You can see here in the equation that we have 3 things that are similar. If you look at each one of them, this part, what is this? Did we see it something like that before? This is a linear function. This looks exactly like the linear regression model. Okay, so it seems like there are 3 linear functions here. This is one, this is second, this is third. Okay, and each one of these are applied to the activation function, right? Because you see A of this, A of this, A of this, right? The output of the activation function is called a hidden unit. So each one of these is called the hidden unit. So we have 3 hidden units in this model. So the hidden unit is a linear function, okay, applied to the activation function, or applied by the activation function as an input to the activation function. Okay, we call the first H1, H2, H3. These are the hidden units. And then if we now plug in H1 and H2 and H3 in the original function, we'll get this. So now we have phi 1 multiplied by H1 plus phi 2 multiplied by H2 plus phi 3 multiplied by H3 plus phi 0. So it's like we are scaling the values of the hidden units, right? Adding them together and adding another parameter, another value. Okay, now let's look at every single step. Actually, you will have 4 parts. First, so let's break it further. First, we will look at the linear functions. So these are the 3 linear functions. As we saw before, this is a linear function, so it would be a line, right? So the first one can be like this, the second can be like that, the third can be like that. Okay, which lines exactly? It depends on the values. From now on here, in this lecture, we will assume that we know already the values of the parameters. We will just want to understand the behavior of the function. Okay, assuming that we know already the values of the parameters. Okay, so depending on theta 1, 0 and theta 1, 1, we'll have this line. So do we know anything about theta 1, 0 and theta 1, 1 from that line now? So how about theta 1, 0? What is theta 1, 0? It's the y-intercept, right? So it is probably minus 0.2 probably. Yeah, right? But how about theta 1, 1? It's the slope. Okay, it looks like a positive, of course, and probably is less than 1. Okay, right. Here, this is the y-intercept again is theta 2, 0, and the slope is theta 2, 1, and it is positive. And I think the slope here is larger than the previous one. How about this one? Negative slope, and the y-intercept is high. Okay, we saw this last time. These are just lines. Yeah, we will assume that we know the values, of course, right? We know the values of the parameters. Here we just want to understand. No. This is not the best. This is just one example of the model. Okay, the goal today is to understand the behavior of the function. Okay, it's not about training. Let's assume that we trained already. We have these values. Okay, whether it's the best or not, we don't care, but how it will work. So that's the first step. It's a linear function, 1 per hidden unit. Okay, after the linear function, we apply it to the activation function, right? So what do you expect will happen if we apply, for example, this one to the ReLU function? Remember, the ReLU function clips the negative part at 0 and passes the positive part. Yeah, so the negative part will be 0 and the positive will be the same. It will not change. That's exactly what we will see here. Okay, so the negative part is gone. It's now 0 and the positive stays the same. Same here. Negative is gone, positive is the same. Okay, so it's like clipping the negative part. For the third one, it's the same concept. The positive part, okay, it stays the same, and the negative part is clipped. So this is the second step. So the first thing, the linear function. Okay, then the linear function is applied to the ReLU function, right? And that's the output from the ReLU function. Actually, these are the hidden units. These are the values of the hidden units. Okay, these are the values of the hidden units. Okay, now are these values linear? Of course, no. Now they are no longer linear because of the activation function. Okay, so the activation function makes them non-linear. Type, yes. Very good question. Um, let me generalize the question to what is the aim of the activation function. Okay, in general. So one of the main goals of the activation function is to make the output eventually to be nonlinear, so that it can fit nonlinear functions. As we said, life is very complex, right? Life is not linear. Not everything will be linear in the problems that we will see. So we need a way, a mechanism to make the output nonlinear. One of them is to use the radio function. Okay, but there are many other functions, by the way, into nonlinear function. Yes, in general, yes, exactly. And what happens? Imagine if the activation function is linear. It will be applied to the input, but the output will be no. It will not be wrong. It will be. And imagine that the radio, not the radio function. Imagine that the activation function is just a linear function. It is another linear function. So we apply a linear function to a linear input. What will be the output? Linear. Okay, so we still have a linear. So at the end, we don't need to have this lecture if the activation function is linear, because at the end it will be a line. Whatever you do, as long as whatever you do is linear, the output is linear. Okay, but now it's a different story. So that's now the second step. What's after that? Remember the original model. We have a linear function. The linear function is applied to an activation function. Then we add. So that's now the hidden unit, right? Now we add the hidden units together. No, before we add the hidden units, we multiply by a scale, by a weight. Okay, so we scale the activation, the hidden unit. Okay, so scaling means we multiply by a constant. Okay, now when we multiply by a constant, we multiply something like that by a constant, what will happen? Let's say the constant is positive. The zero part, the clipped part, what will happen to it? It will stay zero, right? Zero times positive is zero. But how about the other part that's not clipped? It will be scaled, okay, based on the weight. If the weight is higher than 1, the values will increase. If it's less than 1, it will decrease. Okay, if it's negative, it will reverse the sign. Okay, and that's exactly what happens here. So look at this. Okay, this is now, so in the first row, that's the h1, and this is h2, and this is h3. Now we multiply by h1 by phi1, we will get this one. Okay, now can you guess if phi1 is positive or negative? It's negative. It's negative because the sign has changed. And how about the second one? It's positive. Positive more greater than 1 or less than 1? Greater than 1, because it seems like the value is increased. How about this one? Positive less than 1. Okay. There was a question here. Yes. No. These are not vectors. We are multiplying by a scalar. Yeah. So it's just a multiplication. Yeah. Yes. This one. Why that? There's no negative here. Oh, you mean this one? Ah, okay. Because when we multiply by a value, this value, if the value is negative, then we are multiplying positive value with a negative value. The result is negative, right? Right. So it switched the sign. I think you had a question. or it's done?
I think I didn't write it down, so I forgot.
Okay, yes. Is what? Phi 3 is? It doesn't look like 1. If it's 1, then it has no effect, right? It doesn't change the value. But I think the value changed here. It was, I think, lower than before, right? Yeah, you can see that even the y-intercept was high, is higher, is lower now. Okay, so it looks like we scaled it down, right? Okay, other questions? Type. What remains is to sum these. Okay, let me get back here. Sum these. Okay, after scaling, we sum them and add the final offset, the final constant, right? Forget about the final constant. When we add these functions together, what will happen? Yani, now we have these three functions, right? And we just add them. What will happen?
These two are gonna cancel each other, no?
It might be, but in general, what will happen? We will have linear regions, right? Linear regions. In each region, we probably add the slopes of the lines in this region. Okay, let me show you the example here. For these three, forget about phi 0 now. We are just adding phi 1 h1 plus phi 2 h2 plus phi 3 h3. These values are already these. Khalas, this is phi 1 h1 after scaling. Okay, now we are just adding these three. Okay, now when we add them in every region marked with the joints, we will add the slopes. So first of all, if you look at the output here, you will see these breaks, right? Breaking points. We call them joints. Okay? Type. Why did we get these joints? Because the function is not continuous at these points, right? What is the source of this continuity? Why did we get this discontinuity? Because of the clipping that happens, right? Because of these clips, right? Because of these joints. We call these joints. So for every joint in the hidden units, we will have a corresponding joint in the output function. When we add them, this joint will also appear. So for example, you see this? Okay, the value of x here may be 0.5. You will see here at 0.5 also, we have a joint. Okay, here we have this because of this one. Okay, and we have this because of this one. Okay, now it's the same at the same x values. Okay, now how about the slope? If you look at this region, okay, from 0 to, let's assume that this is 0.5. Okay, from 0 to 0.5, yeah, we add the slopes. This is what's that slope? 0. What's that slope? 0. It will be that slope. Exactly. It is exactly that slope. And the same for the others. Okay, the same for the others. Okay, and that's why we will have this shape. This is what we call piecewise linear function. It's a sequence of small linear pieces. The slope of each piece depends on the slope of each function at that region. Okay? Right. This is when we add the three functions together, right? But still we have one small step. Phi 0. When we add, phi 0 is a constant, right? It's considered like a constant. It's just a number, right? When we add a number to another value, what will happen? No, not scaling. It will either raise it up or lower it down. Okay, so just moving the curve depending on the value of phi 0. If phi 0 is positive, you see that the curve has moved up. Okay, and if it's negative, it moves down. So this is to give flexibility on where we want the curve exactly. Okay, so that's, I think now you understand how we can get something like that. Again, this is piecewise linear function with three joints. Why it is with three joints? Because we have three hidden units. Hidden units. Each hidden unit has a joint or contributed with a joint in the final output. And that's why we could have these three functions. Remember in the first slide I showed you these three examples. These are three examples depending on the values of what? The values of what? The parameters. The parameters. Whenever we change the values of the parameters, we will have a different function like that. Is that line? Much more complex than a line, right? Okay. Much more complex than a line. And of course, a network or a shallow network doesn't have to have only three hidden units. It can have much more. But it's the same concept. Each one has a linear function applied to an activation function. Then we add them together. Then we add, before we add them, we scale each one. And then we add them. Then we add the offset, the final offset. Piecewise linear. Yes, it will always be a piecewise linear function. No, it is a curve, by the way, but it's a piecewise linear. It's not smooth, you mean? It's not smooth. We'll talk about that later today. Okay? Yes. Yeah, there are many others. Oh, no, of course that's not. It's not personal. And in reality, there are types of problems or types of outputs for which we choose specific activation functions. Okay, and there are other factors also like whether the activation function will make the training much faster or not. We'll talk about that later, inshallah. Okay, any question on that? So again, this is piecewise linear functions, one joint per ReLU function. Okay, now let's talk about the value or the slope of each linear region. We call the slope here following an activation pattern. What does that mean? If you look at this region, for example, the shaded one, okay? For that region, every hidden unit is either active, which means it has non-zero value, or inactive, which means has zero value. So every piece, every line here, every region has some hidden units active and some inactive. Let's look at this let's look at this shaded region. For that region, which units are active and which are not? How about H1? H1 is active because it's non-zero, right? In that region, it's non-zero. So it's active. How about H2? Inactive. How about H3? Active. Why is it H2 inactive? Because it's zero at that region. Okay? So this is what we call the activation pattern for this region. And you'll find that for every region, some of the hidden units might be active and some might be inactive. Type. How about the next one? How about this one? What do you think? This one. What is the activation pattern here? Which hidden units are active? All of them, and none are inactive. How about the last one? H1 is active, H2 is active, H3 is inactive. Question. with it's not active because it's not affecting the output. يعني let me show you. For the first piece, okay, what actually affects the output, the final output? No, I mean here for this piece, what makes it like that? What affects the output for that region? Is it the first hidden unit, second hidden unit, third hidden unit? The first one has no effect because it's zero. So it doesn't add or doesn't change anything in the output. Okay. The second one, the same. So only the third one is active. Okay. Active here means it actually affects, it has an effect on the output. Okay. So you can see each region has a pattern. In each region, some of the hidden units are active and others might not active. Okay. So I think we already answered this, which hidden units are activated in the shaded region. Okay. No one asked me where's the network here. We call it neural network. Where's the neural and where's the network? Okay. Usually when machine learning courses or specifically deep learning courses are taught and we talk about neural networks, the traditional way to teach it is to talk about history first and why they are called neural networks and why they are neural and how this is related to how our brain works. Okay, I think we don't know yet how the brain works, and this is not how the brain works. Okay, but the guys who thought about that first, they were trying to mimic what they think or how they think the brain works. But nowadays, it has nothing to do, I think, with what the brain works. But still, we use the word neural. Okay. Second, um, we focus here on understanding how the model works. If I told you this is neural network and this is how the brain works, you might think that this is something that is beyond what we can really understand. But it is eventually an equation. Any model, whether it's neural network or not, any learning model, it's eventually is an equation. Whether this equation is very simple or very complex, it's an equation at the end or a function at the end, and we are fitting that function to whatever data that we have. Okay, so it's important first to tell you that a neural network is an equation, but it's important to know how this equation works or how this function behaves, and then I can tell you now why it is called a network. Okay, but I won't tell you why it's called neural. Okay, because I don't think it matters to us. Now, why is it called a network? Because we usually draw it as a network. Okay, actually, this is the model that we saw. These are the hidden units, and this is the output. And we depict or draw this model as a network like that. Okay, we have the input here. We have the hidden units. Okay, and we have the output. And the links between these, we can call them neurons or nodes or hidden units, are representing the weights, okay, or the parameters, the slopes actually. Okay, so far we use them as slopes, right? The parameter that is multiplied by the input directly. Okay, so for example here x, okay, will be multiplied by from the equation here is theta 1 1. So this link represents theta 1 1. Okay, this link represents theta 2 1. This link represents theta 3 1. But then we also want to add the offset, right? Okay, so we add it by same notion. We have 1 here multiplied by theta 1 0. So this is like adding theta 1 0. And at every hidden unit, we sum together the input multiplied by the weight. Okay, so here this is x. So for each one, this is x multiplied by whatever the weight here, which is theta 1 plus 1 multiplied by theta 10. Then we apply the activation function. Okay, so this is the activation function, yes, and the output out of this node is the hidden unit, is applying the activation function to the input. Do you understand this network now, or it's still not clear? Okay, so these are the slopes. So the black lines are the slopes, the brown lines are the offsets. Okay, the slopes, we call them weights. We will no longer say slopes, they are weights. Okay, and the offsets, we call them biases. Okay, and that's the terminology that we would use. And usually we don't add any biases to the network. I mean, we don't add it to the drawing of the network. Okay, they are there by default. Okay, but we just represent the weights by the links. Okay, so again, some terminology. These are the weights or the parameters. These are neurons or hidden units. Usually we look at the network in layers. This is the input layer. We always have one input layer and one output layer and one or more hidden layers. In shallow neural networks, it's just one hidden layer. That's why we call it shallow. Okay, so we have just one hidden layer here, one input, of course, and one output. Yes? Yeah, so far, the input layer has multiple inputs in general. But so far, because we are talking about this example, it's just one input and one output. We didn't yet generalize to more, but we will, inshallah. Okay? Yes. Can I just finish this slide and then take your question? So again, the offsets are the biases, slopes are the weights. The values after the ReLU, we call them activations. And after we apply the ReLU function, we call the value activation. And before we apply the ReLU function, that's the linear part, we call it pre-activations. Okay, so if we go back here, theta 10 plus theta 11 times x, this is the pre-activation value. Applying the activation function to it, we get the activation value. Okay, before and after. So that's, and as we said, the shallow neural network is just one hidden layer. And if we have more than one hidden layer, we call it deep neural network. Okay, and of course, in neural networks in general, we can change the number of hidden units. As we increase the number of hidden units, we increase what we call the network capacity. Okay, yani, if I ask you, if I add more hidden units, will that make the network more complex or more flexible? Why? No, more hidden units doesn't mean more data. It means more parameters. More parameters. And when we have more parameters, that gives us more flexibility to fit more complex problems. Okay, that's why the number of hidden units represent somehow or indicates somehow the capacity of the network. Okay, yes. Sure. Here? Yeah. Yeah, phi 0 is an offset of, if you go back here, it's an offset that is added to for the value of y. It's like it's a bias for y. Okay, remember that we are representing these equations, right? So to represent y, And we said that for every node like that, we sum the inputs and then add the bias. Okay, so we sum. Actually, in general, we sum the input for this figure. We sum the inputs. So we sum the output of this scaled by or multiplied by the weight, plus the output of this multiplied by the weight, plus the output of this multiplied by the weight. This is the part from here to here. But then we need to add this also, right? So to make it general, we just multiply it by 1, so that it looks like we are always adding, multiplying the source. In general, multiply the weight by the source and adding it to the target. Okay, and to just make it constant like that, we multiply by 1. But in reality, we don't do that. I mean, we don't draw it like that. We just draw the hidden units, the input, output, and the hidden units. And we assume that we know that for every hidden unit and for the output, there is a bias always added to the input. So the parameters of the network with this terminology, what are the parameters of the network? The biases and the weights. And that's the terminology that we will use. We will never say y offsets or slopes. Alas, okay? You understand how it works? We will just say weights and biases. Okay. Quick poll. In one input, one output shallow network, which is the one that we discussed today, if we have 5 hidden units, then the number of joints in the output function is 5. The number of linear regions in the output function is 5. The maximum number of joints in the output function is 5. The maximum number of linear regions in the output function is 5. Which of these, if any, is correct? Let's take one by one. How about the first one? If we have 5 hidden units, the number of joints in the output function is 5? Not always. Why it's not always? Now, and we said that every hidden unit has a joint, right? Because of the activation function, the radio function, right? Will that contribute to a new joint in the output function? Always? Why not? No, but we have 5 hidden units, right? Each hidden unit is broken somewhere. Each hidden unit has a joint. So does that mean that this will give us an output with 5 joints? When we sum them, you mean when we sum the slopes, it might not change from the previous one, so it doesn't look as a joint. But there is even easier reason than that, and I think more clear. What if 2 joints are aligned together? And if we get back here, okay, here, this function is clipped here, right, at 0.5. Maybe this function also will be clipped at 0.5. So each one has a joint, but they are all the same. So they will point to the same joint in the output function, right? So we don't have to have 5, but we have to have maximum of 5. So the maximum will be 5, but we might have 5, we might have 4, we might have 3, depending on the alignment and also the slopes. Maybe some slopes will cancel each other. So the maximum is 5 if they are all different. If we have 5 different joints, okay, probably we'll have 5 joints, okay, if the slopes will be different. Yes. Not 3 hidden layers, 3 hidden units, all in one layer. We call it that one layer. Okay, we didn't talk about more layers yet. Okay, is that clear now? So back to the question. So the first one is true or false? False, because it might not be 5, right? Type. Then the second one, the number of linear regions in the output function is 5. Yeah, not necessarily. Not necessarily. The maximum number of joints is 5. Do you agree now? Did you understand it? Why? Okay. The last one. Very good. 5 joints, yes. Then then how many linear regions we will have? How many? Okay, let's get back to the function that we saw before. How many linear regions we have here? 4. How many joints? 3. When we have 3 joints, we will have 4 regions. When we have 5 joints, 6. So is that the maximum number of linear regions in this case, or that's the actual linear regions? In general, if we have 5 hidden units, maximum with the actual. And we said that we have maximum of 5. So maximum 5 joints, right? That translates to maximum 6 linear regions. What if we say the number of linear regions is 6? Again, it's the maximum. Okay, we cannot guarantee if we have 6. Okay, so the maximum joins 5, maximum linear regions 6. Is that clear? Yeah, the maximum is always plus 1 because if you think about it, 5 joins means 6. No, right. Okay. Another question. A linear region can have 0 active hidden units, only 1 active hidden unit, all hidden units active. All of them are correct? So we can have 0 active hidden units in one region. Can we have 1 only? It can happen. It can happen that all of them are active? Yes, so all of them are correct. Very good. Okay. Right. How many parameters are in a shallow network with 1 input, 6 hidden units, and 1 output? Think about that. Okay. How many parameters are in a shallow network with 1 input, 6 hidden units, and 1 output? So 1 input and 1 output, like what we saw, right? That's what we studied today. 6 hidden units. First, how can we draw this? So we have 1 input and 1, 2, 3, 4, 5, 6, right? We have links like that. And then we have 1 output, right? 1, 2, 3, 4. Okay, so that's the input, that's the output, and that's the hidden layer. How many parameters we have? Yes? 19. Okay, why? So you said 19, right? Okay, let's see. Why? 1 is what? Let's talk in the terminology. Okay, so in the terminology we have weights and biases. That we said that parameters are weights and biases. Anything else other than that? No. So how many weights and how many biases? So which 6 weights? So these are 6, right? So we have 6 weights. So this is the weights. 6, which are these. Any other weights? How about these? These are not weights. They are also weights, right? They are weights also. These are weights multiplied by x, and these weights are the weights for multiplied by the hidden unit, right? Remember they were theta and phi, so these are thetas and these are phi's, right? These are the scaling. This is the scaling of the output of the hidden unit, and these are the parts of the linear functions. Okay, so we have 6 plus 6 weights. Any other weights? Any other weights? No. How about the biases? Only 1 bias? We have 1 bias for each hidden unit. So usually we do that to indicate biases. Okay. So these are the biases. How many biases we have? 6 plus 1 here also. Okay. So we have 6 plus 1. So Or what exactly? Okay. So the question is, does that represent one network or what? Yes, that's the network. But there are things that are implicit here because this is a way that's the usual way to draw neural networks. We don't draw biases, we just draw the weights. But we know that for every neuron we have a bias except the input. No. Okay, let me show you. Where is the equation? These are the equation, right? This is the equation, right? Where are the biases? Where are the weights here? Not only the slopes. These are weights, and also these are weights. Anything that is multiplied by the input is the weight. Is a weight. Okay. So thetas, these are thetas. Phi's, these are phi's. But where are the biases? For no, in the equation. This is a bias. These are the biases. Only, and this one also. Okay. So we have a bias for each node or neuron, whatever you call it, for each hidden unit and the output also. Okay, did we say anything about perceptron here? We didn't. We didn't. Okay, don't confuse yourself. Okay, perceptron is just one neuron, just one neuron, not one layer. One neuron only is called perceptron. Okay, so again, these are the weights. So we can write here theta 1 0. No, sorry, theta 1 1, and this one is theta 2 1, and this one is theta 3 1. And how about this? No, no. Phi 1, phi 2, phi 3. طب where is theta 1 0? Yeah, yeah. Theta 1 0 is the bias. Yeah. And so on. And where is phi 0? On y. Okay. Actually, the ones written here are the biases only. Yeah, not the parameters. The other links that are unnamed are actually the weights. Ah, you mean in inference? It depends on, of course, the value of x. The value of x will determine which hidden unit is active. Depending on the value of x, the value of x will determine which hidden units are active, and thus which of them will affect the value of the output. Okay. Any other questions? Okay. Now let's talk about very important property of neural networks in general. Okay, not only shallow, but we'll talk about shallow now. It's called universal approximation theorem. What do we mean by that? This is what we studied so far in the lecture. Has only 3 hidden units, right? Right? But can we expand that or extend that to any number of hidden units? What should we change in this equation? Yeah, let's say مثلا we have 10 hidden units. What should we do? What will be the model? We'll add more hidden units here. And how about this? We also sum more, right? So in general, when we have d hidden units, each one will be exactly the same, similar. It's linear function, and then applying the activation function. And then here, we will just add all of them. Scaling after weighting, of course. Okay? So that's the shallow neural network in general. with d hidden units. طيب, you saw the network with 3 hidden units, right? طيب, if we add more hidden units, what will happen to the function? More linear pieces, you mean? More linear regions. But when we add more linear regions, what will be the effect? It will get smoother over time, right? When we add, and thus it can represent more complex functions. Okay, so let me show you an example. Actually, the example is here. Let's say that this is the dotted curve here is the actual function that we want to fit. If we have if we fit it with 5 linear regions, we can have something like that. Remember, all of them are linear, right? If we have 10 linear regions, it will be even better, right? If we have 20, it's almost exactly the function, right? Okay. If we have more complex function, adding more hidden units, eventually we will get to it, right? So in general, we can describe any 1D function to arbitrary accuracy, to some accuracy. Of course, it won't be exactly the same, right? Because eventually this is linear, right? This is piecewise linear. It's not 100% smooth, right? Of course, when we add more, it will look like smooth, but eventually it's piecewise linear. Okay, so there might be some difference between the model that we have and the actual function if the function is not piecewise linear. Okay, but it will match it to a great extent. So this is what we mean by the universal approximation theorem. With enough hidden units, a shallow neural network can describe any continuous function on a compact subset of the real number line to arbitrary precision, to specific accuracy. Okay, which means that we can do anything with a shallow neural network. But the key point here is specific word here in the theorem. Can you tell me which word here is the key point? With enough, very good, with enough hidden units. Can we in advance know what is enough? Maybe the enough will be million, billion, okay? We don't know, but with enough, we can reach it, okay? How many? Maybe that will be very expensive to do, okay? And that's why, inshallah, we will talk about deep networks. But with shallow, we can, theoretically, we can do everything. Okay, any question about that? Okay, we will inshallah continue next time.